This is the lecture we gave in Beijing, but this was actually given by my student Berta. Well, she's not my student anymore, but she was at the time. So in this lecture, we're going to talk mainly about the practicalities. Of course, there's an awful lot more you can do with microscopy, and I could probably spend a whole day talking on different things you could do with microscopy. So we haven't got time to put everything in. But we'll try and talk about the essentials and mainly the practical essentials of how to prepare samples and how to get good polish. So scanning electron microscopy is the most used. It's the most widely available. Probably about 80% of the lecture is going to be about that, and then just a little tiny bit at the end about transmissional electron microscopy. And scanning electron microscopy is a very rich technique because you have a lot of different signals in the SEM. So this is demonstrated here. The idea is you have an incoming beam of electrons, and then this interacts with the sample. And these lines here, this is from a kind of Monte Carlo simulation. You now have very nice freely available software to do these kind of calculations, which shows the trajectories of these electrons in the sample. And you can see that the electrons are actually going quite deep into the sample before all their energy is dissipated. Typically for the kind of materials we have in cement, which have relatively low atomic weights, we'll have an interaction volume of 1 to 3 microns. But what's very important, it doesn't mean all the signals are coming from all that volume. Generally, we're talking about 3 types of signal, which we'll go into in more detail here. We're talking about secondary electrons. And because the secondary electrons have very low energy, they only get detected from near the surface. Secondary electrons are actually generated everywhere, but deeper in, they never get out again, so you can't detect them. Then backscattered electrons, they have similar energy to the incoming electron so that they can be detected from greater depth. And finally, X-rays. X-rays are not absorbed very much by matter. That's why we can do X-ray diffraction. That's why you can do an X-ray of your body. I mean, you can shine X-rays right the way through your body. So they're not interacting very much with the matter, and therefore the characteristic X-rays are detected from a much larger volume, and that's where we have the biggest problem of the resolution. And even for the, say, the backscattered electron, it looks very much worse in this diagram here, the difference between secondary and backscattered, but it's a question of statistics that most of the backscattered electrons are coming from just very, very close to the incoming beam. And you've got a distribution that falls off very quickly as you get further away. So let's look at these signals in turn and what we can do with them. So this is secondary electrons. They're generated from what's called inelastic scattering. So an electron comes in, it bumps out another electron from the atom. These, because they have much lower energy, they are only emitted from the surface, and the intensity of their emission is kind of proportional to the inclination. And this is why, you know, I mean, you've all seen these classic pictures of flies in the electron microscope and things like that. You get very nice pictures of like the outside surface of things. And also the way that the electrons is detected, you know, because you have a charge detector here, that even if this electron's coming off like this, it will be taken into the detector. You get what's called this shadowless imaging, which is actually quite similar to the way we see things visually. So the secondary electrons, people like them because they kind of look like you're really seeing things, like you see things with light, okay? So how can we use them in cement paste? Well, generally we use them, have to have a rough surface, because the whole point if a surface is flat, you don't get this differential scattering very much. And fracture surface you can make very easily. You can just smash your sample with a hammer, you can pick up a little bit, you can put it in an electron microscope, you can do it in like 5 minutes, and that's kind of the problem. It's so easy, people are doing it all the time, even though, unfortunately, in 90% of, or 99% of the cases of secondary electrons images that are in published papers, it's probably a waste of time. So how can we use it? Well, you've got nice high resolution. You can see your morphology of your hydration products, and it's very good at young ages. But first and foremost, it's not representative. You've made a fracture here, so you're fracturing through weak areas. And you've got no chemical analysis. People are always making the mistake of thinking you can do chemical analysis on fracture surfaces. You can't. It's wildly inaccurate. And you've got no quantification. So this is what you can see. I mean, this is a nice image. This is in a high-resolution microscope. You see we're down to 500 nanometers here. We can see this is the surface of a cement grain at very early ages. And we see we've got these nice little rods of ettringite, and we've got these lumps of CSH. And, you know, we can see a lot of important things. For example, this ettringite here, we can see how small these rods are. So we can see that the fact that C3A hydration is slowing down with sulfate is nothing to do with ettringite being there. You know, people talk about an ettringite shell. There's no way that little rod of ettringite is stopping that grain hydrating, okay? It's much more subtle. It's absorption of sulfate, okay? We can see the CSH, and as we go on, we can see very nicely how this CSH is developing on the surface and then grows through this main heat hydration peak. And this can help us to put together kinetic models of the hydration. So that's some examples of how I think it's useful, but I would say it's really generally not useful after about 1 day. And unfortunately, this is an example I took from a paper. I won't tell you what paper. I can't even remember what now, and I hope the person who wrote that paper never finds out that I did this. But this is a typical example of somebody claiming to have done some useful scanning electron microscopy. And these were supposedly 4 different samples. And these images are telling us why these samples are different. Well, I mean, you know, it's a joke. This is an aggregate particle here. So you can see you've got different amounts of aggregate particles. In all these samples, you can see you've got porous areas where you've got little spiky things, like here. But you've also got areas where you just see this dense mass. And this was a complete waste of time, absolute complete waste of time. But 9 studies out of 10 are the same. People are studying cement. The person down in the next lab said, oh, we've got this scanning electron microscope. They try to do this kind of picture, but it's a waste of time. Please don't do it, okay? Because it really upsets me that there's so much time, instrument time, human time, wasted on these kinds of things. Much more useful are backscattered electrons. There was a nice little animation that showed how it happened, but that's what caused the repair problem on the file this morning. We nearly couldn't have the lecture at all. But you have these electrons here that come down and occasionally get bounced back by the electrons of the atoms. And this is a very nice technique because it means that the contrast, the intensity depends on the atomic numbers. And this leads to what's called phase contrast. So the classic thing you can see, this is a typical backscattered electron imaging. It's maybe a bit dark, but you can first and foremost see the unreacted cement. So this is brightest because the average atomic number, this has got no water in it, it's just calcium silicate. This is the brightest. And then we can see the calcium hydroxide, nice areas of calcium hydroxide, which is the next brightest. And then we can see the other hydration products. So we can generally identify this nice even CSH around the cement grains, and then this rather less well-defined CSH, but also will contain ettringite and AFM phases out there. And of course, the black areas are pores. So you've got a section that's representative because you've polished it, and you can look at very large areas of sample. So you can have absolutely representative things. You can identify all the different phases. You can quantify them, as we're going to discuss later. And you can see a whole lot of information about, how the grains have reacted, all sorts of other things. So this is really, really very useful technique. And then the third one is characteristic X-rays, where you have the X-rays. The animation works in this case for reasons I don't know. And then you have an electron that falls back to an inner shell and ejects an X-ray. And this can be useful to tell what phases you have. You have to be aware that these X-rays are coming from the whole volume, from the whole 3-micron volume maybe. And then you have the problem of deconvoluting all these different signals. Before we go on and look at some examples of how this is used, just a word about environmental microscopy. Now, all the manufacturers of environmental electron microscopes hate me because it's a total waste of time in cement studies. They give you the idea that you can mix your cement and you just put it in the thing and you can see through water. You can't see through water. Electrons cannot pass through water, well, not more than a micron or so. So you have to remove the water, and once you've removed the water, it's dry sample at any rate. And there's crazy things people did where they sort of had a sample, they wetted it and then removed the water and then re-wetted it. This is just terrible because hydration is an intimate system of the pore solution and the solids. If you keep removing the water and then put it back and removing and putting it back, you've got something completely different. Okay? So, repeated wetting and drying is not realistic hydration conditions. You don't need an electron microscope. This is a nice example. This is a picture I took in 1981 in my PhD thesis. This is a fracture surface done in high vacuum. It was gold coated. And this is a picture one of my students took in 2012. She did it in a very nice low voltage, uncoated, everything. And basically you see they're the same. Okay, if you look at the fine detail, it may be a little bit different, but it's basically the same. Okay? So don't be taken in by any of this blah, blah about, environmental microscopes and anything like that. And if you look at stopping hydration, you also see that you can use most techniques. They don't make a difference. So here we compare freeze drying with isopropanol. So from point of view of things like X-ray diffraction or MIP, this technique is much, much better. But from point of view of microscopy, it makes no difference. So if all you want to do is to see what you've got in the sample, you see that it really makes no difference. And you can use most of these stopping techniques, but still don't dry at 105, because that's still going to make a mess of your sample. Okay? So my method has little impact on the images. It will impact the other techniques as we've seen. And even ettringite, in ettringite, which you hardly have to sneeze at for it to lose its water, the morphology is well preserved, as we saw in this image back here. So this is perfectly good for identifying ettringite. That ettringite has lost all its water and it's lost its crystal structure. So, but it still looks the same. Then polishing. Now, this is the problem. I give this lecture and everybody says, oh, this is nice. I'm going to use backscattered electron imaging. Unfortunately, they don't realize that the big problem is polishing. It's difficult, and you really have to learn it. You really have to learn it with somebody who's done it before. And this is the basic equipment. So you've got a polishing disc, you've got diamond sprays. Don't polish with water for, I hope, obvious reasons. We now use deodorized petrol. The problem with all of these kind of liquids you can use for lubrication is many of them may pick up water. So many of them, if they pick up water, they're the same as using water, and you can get etching of your samples. So this is some of the problems you may typically have. This is a backscattered electron mode. This is the secondary electron mode. So in the secondary electron mode, we may quite clearly see the small holes, and we can see a scratch. But actually, this is a very good sample. Okay, so that's about as good as you'll get. Beware that you can often have bits of dust. You should be very careful about the way you treat your samples. Don't leave them around on the lab bench. But this is really pretty good, and you can see all the phases we talked about before at quite high magnification. And this is what many, many people end up with. And, you know, sometimes we end up with that and we don't know why it's all gone wrong. This is the problem. It's not easy. But look between that, you can see all your anhydrous phases, you can see your calcium hydroxide and everything. And here you can kind of see an anhydrous phase, but it's really ragged, and the rest of it's just a mess. Okay? And that's very, very easy to get. You've got erosion of the sample. You can't really identify the different hydrates or anything. You know, it's just hopeless. You can't really see any calcium hydroxide there at all. This sample, you know, was not so bad. Most of it, we can see the calcium hydroxide quite well, but look at these anhydrous grains. They've been completely etched away. And again, it can happen for reasons you just don't understand. And once this has happened, you've got, just don't bother to carry on with the microscope. Just stop, you know, because, I mean, we had a very nice paper where people had done image analysis, and they showed an image, and it's like this. You know, it's a waste of time. Waste of time. This is another problem you get typically in very young paste. You do have a problem that before about 10, 15 hours, it's very difficult to polish samples. So this is an example of a paste that was only a few hours old. You can start to see the hydrates, but you see you've got a lot of roughness that has emerged, and you've probably destroyed a lot of your paste. Particularly difficult, of course, then is if you move to concrete. And I said at the beginning that the one real advantage of microscopy is you can do it on concretes and mortars, but you have even more problems of polishing. And this is the very common problem of polishing. The paste is fairly okay polished, but we've got this kind of erosion around the aggregates. And this is because the aggregates are much harder than the paste, so you tend to get this preferential polishing. And it is very difficult. The most important thing is to impregnate with resin, but usually the resin doesn't go in very much, so you have to impregnate maybe more than once. And this is all described in the book, and this really summarizes, you know, what we've learned from experience. So really the best way is to learn by walking alongside somebody with experience. And we quite often have people who come to our lab for a month or 2 months just to learn how to polish samples, hopefully to do some other things, but, you know, within reason, we're quite happy to have people. Resin impregnation is really essential, and you should really do that. You should cut your sample roughly, then impregnate the sample, and then polish. It's no good trying to impregnate the whole sample and polish. You've got to allow your resin good time to set. This is generally taking 1 week for it to set. You need to grind, before you start polishing, you need to grind very carefully, generally by hand, to get a very flat surface with minimal removal of the material, so the resin doesn't go in very deep. You then, once you've got something flat on a kind of, you know, emery paper, you go through the successive grades. So usually we go like, you know, 10 micron, 5 micron, 1 micron. You can go to quarter, but there's very little difference between a quarter and 1, to be quite honest. At each stage, check your sample. So it's just as easy to polish too much as it is to polish not enough. So use an optical microscope to look at the stage of your sample. Polish a bit, look at it, polish a bit, look at it. You should go to the stage where you can see that the scratches from the stage before are removed. And if you go too far, there's nothing for it. You've got to go back to the grinding flat and you've got to start again. You can't recover it. And the problem is, you know, people say to you, how do you polish your samples? I can tell you how we polish our samples, but every material, every machine is different. So I can't give you a standard protocol. You have to look at it yourself. And you have to know what you expect to see. Do not trust the unexpected. I had a very good example where I was completely fooled myself. Somebody had given me these ancient samples, you know, coming from Roman concrete and something like this. And we had this new polishing machine in the lab, and I put it in the electron microscope, and there was this iron everywhere, no, this lead everywhere. And I said, oh, these Romans, they were putting lead in their concrete. And of course, it was a total artifact. The polishing plate contained lead, and it was picking up polishing stuff, lead from the polishing plate. So it was complete nonsense what I was looking at. So, you know, think what you expect to see. And if you see something unexpected, then it's probably the sample preparation. And don't leave polished samples around. They'll pick up dust and they'll carbonate. So, okay, so if you've done it right, you can get lovely images and you can see all sorts of things. So this shows some examples with slag. And here we can see very clearly the slag grains that haven't reacted. We can actually quantify the slag grains, and we can apply image analysis. By image analysis, we can see the rims around the slag. We can see how these are dark, and the reason they're dark is because they contain all the magnesium that was in the slag. Magnesium has very low mobility, so it doesn't contribute to filling the space between the grains. We can see, you know, we can see how dense the CSH is. Seems that with slag and fly ash we form more kind of compact, less microporous CSH, which we haven't quite determined all the implications of that, but we can see an awful lot of material. We can do analysis on this material to get the composition, so we can get an awful lot of stuff. Here's a fly ash paste, for example. So you can see the variability of the fly ash. You can see this fly ash particle contained quite a lot of crystalline material, which these are the bright crystals, and it started to react between the crystalline material. You can see other fly ash particles have hardly reacted at all. These bright specks, incidentally, were almost certainly specks of dust. So you can really determine a lot, and we've now developed an image analysis technique where we can actually quantify all the different glasses in a fly ash. This is another example with silica fume. Okay, so this shows you the limitations. This is now with silica fume. So now you see we can't identify the individual silica fume particles. Silica fume is really too small. Sometimes you can kind of get an impression on it. You can kind of see this granular appearance here because this is all the silica fume well mixed up with the CSH. But it's really difficult to pick out individual silica fume particles. Some problems, I mean, if you have calcium aluminate or calcium sulfoaluminate cements, which have a lot of ettringite in them, because ettringite has this high water content and it loses this high water content in the vacuum, you'll think that your sample's very cracked. But that's not really a correct impression because this just happened on drying. But these kind of cracking patterns, these are very typical of where you've got masses of ettringite or AFM phase. And you can often pick out, you know, for example, in sulfate attack, you can pick out ettringite for that reason. Now, microanalysis, because they detect this quite large volume, we need to analyze these points in a rather particular way. So first of all, be careful. Don't have a too intense beam because you can see here the damage you can quite easily make when you make the analysis. So you want to keep your accelerating voltage down to about 15 kilovolts. And then you can understand your composition by making these kind of plots. So the two plots that we're using most of this plot of aluminium calcium against silicon calcium, and this one of sulfur calcium against aluminium. And on this one, what we can see here, we see this cluster here, which is the CSH, and then points that lie on this line here will be mixtures of CSH with calcium hydroxide, and then points going up here will be mixtures of CSH with either ettringite, AFT, or AFM monosulfate. It's generally quite difficult to see whether you've got mainly monosulfate or ettringite. For that reason, it's much better to look at this kind of plot where we've got the sulfur, and then we can really see that in this sample we had mainly mixtures with ettringite, which are going up this line here, but you may in some cases have mixtures with monosulfate or with mono or hemicarbonate. So this is the kind of scatter plot, and what we can then do, we can then analyze the what we call pure CSH, so it's the least intermixed CSH, as being the outer point here, because this is the least intermixed point. And there's a paper, I'll give you the reference at the end, which we published this year, which really goes through the whole protocol of doing these analyses and how you can get this analysis of CSH. And this analysis of CSH is then very important because you need that to contribute to your phase quantification. So the next topic we're going to talk about is quantitative image analysis. And first of all, it was proved a very, very long time ago, in 1848, that the volume fraction is the same as the fraction on a surface. So you can guarantee, everybody always asks this question, if you measure the area fraction on a surface, how do you know that it corresponds to the volume fraction? You know that because it was proved mathematically in 1848. And when I say proved mathematically, that's really proved mathematically. That's not just an estimate. Now, of course, you have to take statistics into account, and it depends on the sample being statistically homogeneous and statistically isotropic. And if your paste has been well mixed and prepared, that will be the case. You can also, in fact, look at the line fraction on intercepts. This was proved in 1898. And you can also look at point fraction. So point counting is still used on optical micrographs of clinker, and it works very well for this reason. So you can measure the area fraction on a surface. It's the same as the volume fraction. So we can use image analysis to look at the individual phases, and we can separate them based on their backscattered electron coefficients. So the easiest one to measure is the anhydrous amount. We have, if this is the gray level image, you see the anhydrous is very easy to threshold. We generally do a little bit of cleaning of hole filling and filtering to filter out the small kind of random particles that come up any rate. You see in this particular image you have 16.15% of anhydrous. If you average over, well, it says 100 images, but if you have a very good, very homogeneous paste, you can probably get away with much less. You can then calculate your degree of hydration, because if you have, say, a water-cement ratio of 0.4, the volume fraction of anhydrous at the beginning is about 40%. Now it's 16%, so the degree of hydration is about 70-80%, which is what you expect. And you can use that very well to measure the degree of hydration. It's not as accurate as Rietveld analysis, because Rietveld analysis works very well on the anhydrous phase. So if you want to measure the degree of hydration, this is not the recommended method. But it has the advantage you can do this in a concrete, whereas you can't use Rietveld in a concrete. So if you want to look at the degree of hydration of cement in a concrete, you can use this method.
And then if you have amorphous SAMs, it's also good.
Well, if they're large. So it works very well for slag.
Fly ash, perhaps?
No, slag works very, very well, because slag, as we saw in this image back here, is a nice homogeneous gray phase, and image analysis is probably the best way to estimate slag. Fly ash, the problem is you have all these different gray levels. Yeah. So generally, straightforward image analysis on gray level does not work well for slag. But if you do this chemical quantification that we published last year, then you can make it work. Now, porosity, really you can't measure accurately by image analysis. And I'll come back to that this afternoon when we talk about techniques to measuring porosity. And the problem is, you see, if this is a very high magnification here, and here we're at the limit of the resolution of the backscattered electron imaging. So you can kind of see these ettringite rods, but we're kind of sampling these over a depth. And you know, where's the boundary of this CSH? You can't really say where's the boundary, and then you can't say where's the porosity. And as we're going to talk about this afternoon, the reality is in a well-cured paste, most of the porosity that remains is 10 nanometers in size. And we're nowhere near resolving 10 nanometers in these pictures. This shows the fracture surface, the same problem. You know, what most of the porosity is now between these needles in a well-cured paste. Okay, well, that's of the order of 10 nanometers. So we can, you know, if you want a comparison, you can threshold porosity and you can compare between one sample and another. So if you want to do it for a comparison purpose, it's okay, but don't think it's the real absolute porosity. So as I say, we've imaged the porosity, and what's interesting, you see that an awful lot of these larger pores are actually these hollows that are inside these hydrated grains. And then if you think from a point of view of durability, these are large pores, but they can only be accessed through this CSH. So they may as well be small pores in terms of access, and people make a mistake about that. But you know, here we can see the comparison. This is comparing NMR, which I'll talk about this afternoon, with the SEM, and you can see the amount of porosity. It's less than, well, at the beginning it's about half, but later on it's like even less than that. It's about 20%. We're really measuring hardly any of the porosity. We can use a combination of the gray level imaging plus the image analysis. So I said the image analysis is very good for quantifying slag, but some slags have a gray level that's almost the same as calcium hydroxide. And then you have to couple it with the magnesium map to differentiate between calcium hydroxide and slag. So this is an example actually from a calcium aluminate cement with slag, and you see we've got this very complicated aluminate grain here with lots of different phases here which overlap with the slag. But none of these contain magnesium, so we can then use it to detect out the slag very well, and this works pretty well. So other examples, this fly ash with full spectral maps. This was from Beijing, so it says presentation in conference. You're not at this conference, but you can look up the papers. We've done a lot of work on alkali silica reaction, and that works very well, and we've published a lot of papers on that. And combining information together, a particularly interesting case is this study of sulfate attack, which we published in this paper here. And these references, I think, are mainly in the chapter. Certainly the last two are. I'm not sure if we'd done that by the time we wrote the book. So the key thing about image analysis is statistics. You're only measuring a very small area of the sample, so the homogeneity is very important. And generally you want to not use a standard deviation because one image will naturally vary from another, but use the standard error, which is the standard deviation divided by the square root of n, where n is the number of measurements. And this shows you if you just want to measure degree of hydration, you can get pretty reasonable figures for, say, 20 images, but if you can set up an automatic analysis, you may as well do 100. And if you're going to look at a concrete, well, then you have the problem that you have to edit out the aggregates. We can do that, but it does mean that you need to look at many, many more images. And if you want to look at something like the interfacial transition zone, this is something we did and published, you've got to look at many, many more images. So just to finish, I'm going to say a very, very small amount about transmission electron microscopy. There's much more in the chapter, which you can look at. It's really fantastic when you get a good image, but very limited access to TEMs, very difficult to learn proper specimen preparation. Each time I've had a student who wants to do TEM, it takes them about 1 year to learn how to prepare samples. So don't even think about it unless really you've got a lot of time. You can only look at very small areas, and the main problem, you have a terrible, terrible susceptibility to beam damage. Again, 99% of TEM pictures I get are just beam damaged. And this just shows what can happen in very short time, like 1 minute. This is an image on the left. It's actually a dark field image, so the products are bright and the holes are dark, which is the reverse of what you normally see in TEM images. And just look, here you can see you've got these nice fibrils, and already after a minute, when we took the same area again, you can see how these kind of bubbles are starting to develop. And if you look in published pictures, you can see 90% of them, they've got these bubbles. I even had the unfortunate experience of hearing somebody at a conference talking about saying that these bubbles were the gel pores. But these bubbles are not the gel pores. These bubbles are damaged. So a lot of people waste their time with transmission electron microscopy, which is why I haven't said much in this lecture, because I wouldn't recommend it unless you're working in a lab that's specialized in it. And after training 3 or 4 PhD students, so they spend 1 year learning how to learn it, and then they leave. So I've given up training PhD students anymore. I have a postdoc who does it for everybody, because it's the only way to be efficient, you know. But it can be also very useful on this problem of the CSH composition. So I explained to you earlier with those plots how we have this cluster of points in the SEM. Now, the big advantage of the TEM, you've only got a very thin sample. So they don't have that big interaction volume because there's nowhere for it to be, just in this very thin part. So you can get a very good precision. And here you can see why we now choose the outer edge of this cluster for the composition of the CSH, because by TEM we can see in the unmixed samples that the composition is really pretty close to this outer edge here. And so if you optimize your analytical techniques in the SEM, you can get a result for the CSH that compares very well with TEM, and therefore it's much, much easier to do it by SEM than TEM. This value at the edge of this cloud is a very good approximation, and if you want to learn more about that, that's all published in a lot of detail in this paper in materials characterization.